So let's get back to building out the psi function. We want to get to the new interesting part with the big omega and the true ordinal collapsing nature of this thing. But we got to work up to it. So a next natural place is to look at, let's say, psi of omega 2, omega plus omega, in other words. And we're going to focus on the g function as a way to understand that. So what's going to happen? Well, g of psi of omega plus n, well, what we've seen is that adding 1 each time, that what that does is it just double ups by n. That's what we call the dn operation. So we're going to do that n times on the g. And we know what g of psi of omega was. It was n double up n squared. And we also know that every time we double up by do the dn operation, we add approximately we add n minus 1 to the double up index. We're going to do that n times, and so we're going to get n squared plus n times n minus 1. So the details might not be super important. If you want to sort of pause and convince yourself that that's the story, that's cool. But the main thing is that we're progressively increasing this double up exponent, but not yet radically getting to a new level of bigness for g. I'm going to keep writing this. I'm going to try and write it consistently as n. That was our very starting point. That was n double up n was g of psi of 0, the start of this new story. And what we've done is we've really added 2n copies of n minus 1 to that, because over the whole story from 0 to up to omega 2, we've really just done the same thing 2n times, and that was the dn operation. And each time we added approximately, well, what happened was we added n minus 1 to the double up index. Okay, so really there's another simple rule here. Okay, what's another way to say what's the significance of 2n here? If you start from omega 2 and you look at, fix some n to put into this whole story. So omega 2, like n is 3, omega 2 turns into omega 3. Well, that's not a decrement, that's a limit. But now the first one we really get as a decrement is omega plus 2, then omega plus 1, then omega, and then we go down again. 3, well, that's really just a limit, then 2, 1, 0. That should sound familiar. Every time we actually decrement, every time we actually do a minus 1 and go from a successor ordinal to its previous one, we get another d sub n. Okay, so, and what does that do? It gives us another double up n. So the point is the total number of dn operations is exactly g of omega 2 of n. So that's a really nice thing. This is one of the reasons why I wanted to focus on g, is that even if our primary interest wasn't the g function, and of course our primary interest is the f function if we can wrap our minds around it, the g function actually really is something that comes into this. So this 2n is nothing more nor less than just g of the input to psi. Okay, so really it's a special case of a more general rule, this claim. Okay, and this is going to be another one where we have to be careful, and I can't really literally state this for all alpha. But until we get to something where our understanding of like psi and the successor rule gets changed, what we have is that if you have alpha and if you know what g of alpha is, so if it's some manageable countable ordinal, and again, subject to some stuff we're going to have to be careful about, then g of psi of alpha applied to n is, you start with n double up n, and then you know that the process is just going to, so far at least, is going to just double up that a bunch of times, and the number of times you apply the double up operation, the double up n operation, is exactly just g of alpha itself. Okay, and then there's an approximation for that. We're starting with n double up n, and we're just going to add g of alpha applied to n times n minus 1 to the double up index. That's a really nice rule and takes us not into the new territory for g so much, but takes us a ways towards there. And in fact, I might as well generalize that right off the bat. As long as you can make this a little more general. We'll talk about this a little bit. As long as beta is countable and alpha plus beta is in the normal form where we're not putting like 1 in front of omega, that kind of stuff, then the general version is that if I know two things. If I know psi of g of psi of alpha, whatever alpha is, pretty much, and I know that, I know this whole thing, and then beta is something reasonable, then adding beta to that sucker is going to just dn this g value of psi of alpha, g of beta times. Okay, so you can put in the comments if you want to see more of a proof of that or more examples of that. It's a really nice rule, um, and you can let me know if you want to see more about that. But I'm just going to sort of use that from now on. If you want to know what we really need, I think it's a pretty accurate version of what we need. We really need for all limit ordinals gamma with gamma less than or equal to beta. So not just beta itself, but we need the inductive proof to work all the way up to beta and not have any gaps where it would fail. We need this wonderful thing that alpha plus gamma, the nth term in the fundamental sequence, is just leave alpha alone and apply the bracket n operator to gamma. Okay, so I say very little more about the details of that, but I'm going to start using this rule. Okay, so let's do an example of that. We've got psi of, let's say, omega to the omega, going a bit beyond omega 2. Okay, we should be able to skip a bit because we have this nice rule. Okay, so we first ask, well, what's g of omega to the omega? Ah, that's where we can use our really nice rule that's just n to the n. We already knew that. That's nothing to do with psi. And that's how many double ups we're going to do to g of psi of 0. G of psi of 0 was the n to the double up n part, and then we're adding in n to the n copies of n minus 1. Not a bad approximation for that is ignore the minus 1 and the plus n, and we're getting n double up n to the n plus 1. And probably for most purposes, it's good enough to say n double up n to the n. Okay, so we've made some increase here, and not too surprisingly that this input to psi is getting bigger. Psi is getting bigger as an ordinal. It's a really pretty ginormous ordinal, really, and G is reflecting that in upping this sensitive index of the double up. Still not getting to the triple up level though. Okay, but here's the next one. Okay, well, what's a really good way to create a big ordinal? Good old psi of 0, which is epsilon naught, and then put that into psi. And this is a real hint as to where this is going. Of course, whenever we've got a function that can be iterated, that you can put the output into the input, we're going to try that. And this is the first example where we're doing that with psi. Now, in the kind of traditional notation, that's just epsilon sub epsilon naught. If you list out all the epsilon numbers, the fixed points of the omega to the x function, of the phi naught function in the Veblen language. This is the epsilon naught version of that. Okay, so this is really, if you want Veblen again, I said I wasn't going to do much more Veblen, but this is just phi 1 of phi 1 of 0. One more parenthesis. Okay. All right, so what's that going to be? Well, we look at g of phi of 0 of n. We know what that is. That's n double up n. And we put it into our general rule, and so approximately this is n double up n times n minus 1 plus the measly little n that we started with in this slot. Everything else pretty much goes away. Pretty much that's n double up n. Aha! Finally, we have put the parentheses in the right way. So that's n double up n. We found a way to put that into the exponent slot, or the second slot of the double up. The number of exponents in the tower, really, right? And we're putting that in the right place to make this n triple up 3. So this is where we get n triple up 3. Again, a good place to pause and say, oh my God. I haven't mentioned f explicitly in a while, and I'm going to wait a bit to go back to actually talking about f's and sort of do tiny little bits of expansion. But remember, whenever g goes up by even a little bit, f goes up by a lot. If g goes up significantly, like going up to here, f goes up by a bunch. This is the number of terms in the initial expansion and in every re-expansion when the n gets bigger and bigger and bigger. And now finally that is getting to a triple up. That is pretty scary. So, if you think about, one of the things that people say about a Googleplex, which we all used to think was a big number, right? Is that, if you just write it down, you need more zeros than there are particles in the known universe, like the observable universe, right? So here, This is the number of expansions you'd have to do just at the very, 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 very start to just get any start and connect it down to f sub 0 of n. Even if n is just 3, even if it's 2, really. This is so much more than the particles in the universe. It's not even funny. Okay, so we're talking about something where even just saying, oh well, first I know I can't just I know I can't write down f of 3, f sub psi of 0 of 3, but at least I'll just sort of play with the initial expansion like I did in a lot of the earlier videos. That is such a joke that it's not even funny. Okay, so so now we're finally getting the double ups to be to iterate to be triple ups. Okay. Oh, and here I did put in the Veblen. I forgot I had done that. Okay. So if we want to compare to Veblen, there's the comparison again. All right. So the next step I think is pretty obvious. If we've taken 0, put it into psi, and then put it into psi again, we always do that multiple times, and then we always diagonalize over that index. Okay. So we're going to look at psi of psi of psi of psi of psi of psi of 0, otherwise known as phi1 of phi1 of phi1 of blah, 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 0, or in a better notation, g of psi to the k of 0. Okay. Um, so what's going on with that? Well, what we've seen now is that when we do psi of something and iterate it, the g is now putting the n double up in the right place. Okay, so now we're n double upping that k minus 2 times and starting with an n triple up of 3. Well, that's exactly the definition of n triple up to the k plus 1. Because this, remember, this is n double up n. And so if you count all the n's, you're going to get k plus 1 n's. Okay, so now we're really fully in the general triple up level. Depending on how many psi's we have here, we're going to get that much plus 1 in the powerful index of the triple up. Okay, so what is this ordinal that's like the limit of these guys, right? So this is interesting in itself for some fixed k, and it's a big ordinal, but what about the limit of those guys? Well, of course, that's the standard way of producing the first fixed point of a nice function, to be technical, a normal function of ordinals. You just do it over and over and over again and take the limit, and that's something that doing one more psi won't do anything new for you. Okay, so this isn't anything new, really. This is exactly what Veblen would say. He'd say, well, duh, this is by definition what I'm supposed to do. You've been working with phi1 the whole time. You've been calling it psi, but it's not anything new so far. And guess what? The limit of this guy iterated is exactly how we've been told to define phi2 of 0, the first fixed point of the phi1 function. Okay, so of course that starts on the Veblen story, but this is where we start to diverge. Okay, we've got a different idea of what we should do here. So here's what we're going to do. We're going to say psi of omega, big omega, which is it's essentially a placeholder, but we're going to be very specific. It's the least uncountable ordinal, the initial or first uncountable ordinal. We're going to define psi at that input to be exactly this limit, which if you want to is phi2 of 0. Okay, and more specifically, of course, we want to really talk about the fundamental sequences. So the nth term in the fundamental sequence leading up to psi of omega is, by definition, psi of psi of psi of psi of 0, just exactly the kind of thing here, which we know how to get the g value for. Okay, so big omega is the first uncountable ordinal. Often a sort of more specific name for that is little omega sub 1. I'm not going to use that so much because I want to emphasize how different big omega is and not have you confuse it with little omega, which is the smallest infinite countable ordinal. Okay, so as I said, it's not really, you can build this theory making it pretty much a very wide class of possible things. What's important is that it's bigger than anything we actually want to create. Our purpose here is to create countable ordinals, because those are the only things that can be interpreted as sequences of instructions for repetition, diagonalization, etc. Okay, and so we might as well, if we want something that's guaranteed to be bigger than that, we might as well just make it the first uncountable ordinal. And again, you can indicate in the comments if you want to know more about that story. It's a great, wonderful, famous story about cardinality and stuff like that, but that's not where I'm going. Okay, and here's the key idea. We're going to extend this idea. We created psi of omega by iterating psi, just plain psi. And here's what we're going to do. What we're going to create, we're going to create psi of some arithmetic expression involving omega, like omega squared plus omega plus 2 or something like that, or omega to the omega plus omega squared or something like that, by iterating psi of slightly smaller arithmetic expressions involving omega. It's purposely vague because I want to just do it by examples. Okay. Um, so we're going to do it by explicit examples. I'm going to show every time I'm going to do it by fundamental sequences so that I can then talk about the g values and occasionally go ahead and all the way back to the f, even though it's going to just totally blow our minds. And I'm not going to give you the general definition to start with. Um, it really looks quite different if you start with a general definition. I don't think it's what we want to start with. Okay, but I do have to mention some tricky points. This is getting a little long, but I might as well go ahead with the tricky points and then we'll really be able to grab hold of it in the next video. Okay, so up till now, if we took an ordinal alpha, like 0, 1, 2, little omega, omega to the omega, um, even psi of 0 itself, psi was creating a bigger ordinal than what we put in, which was kind of the whole point, right? We're trying to create big ordinals. Why on earth would we take something already big and make it smaller if the psi is supposed to create new big ordinals? In fact, usually it was much, much greater than what we put in. Like psi of 0 is a heck of a lot bigger than 0. Okay, but we've been using implicitly that psi is continuous this whole time. And this is this thing about fixed points here. Suppose I take psi of big omega. Now I've claimed that I want psi of big omega, this really big ordinal, qualitatively bigger than anything we're actually going to be as our final answer or an output of psi. What if I put that into psi? Okay, well, I gave a definition that psi of big omega was the limit of psi sub n of 0. Okay, then I put that into psi one more time, and again, the Veblen idea was that, oh, hey, that's familiar. That's how you create a fixed point. The proof is simply that if you know psi is continuous, then psi of a limit of something is the limit of the size. It's one of the definitions of continuity. And so that's the limit of psi one more time of 0. But wait a minute. That's just a slightly bigger tower of size. But we're taking the limit as n goes to infinity anyway, so it's just the same thing. This is exactly what we started with. Okay, so not too shocking that psi of omega, which can be Veblen described as phi2 of 0, is a fixed point of psi. Okay, that's just a little bit of a proof of what I mentioned already. But wait a minute. Okay, psi of omega is this countable infinity, this countable ordinal, phi2 of 0. But of course, that's much, much less than omega itself. So this is kind of a weird decision that I've made here to say that psi of big omega is much, much less than omega. Suddenly, that's very different from what we've been expecting from all of our functions that we've done so far. And this is the start of the collapsing part of ordinal collapsing functions. Okay, so that's weird. And then what about the values of psi of alpha between alpha equals this psi of omega, or phi2 of 0? This is a moderately big countable ordinal, but it's not exhausting all the countable ordinals by any means. We're going to create much bigger ones. But what about the values of psi when the input is between that and alpha equals big omega? It turns out that for our purposes, those are not going to be useful for anything as inputs to psi. They're going to be great outputs, but they're not useful for inputs to psi. And the general definition that eventually I'll probably trot out for you, the kind of non-constructive seeming definition or non-explicit one, it just sets psi to be constant for that entire range. That's a little weird, is that we just give up and say, you know what, the interesting stuff for psi after this sort of starter region, which we've been doing for the last few videos, starts at omega, big omega and above. And everything else in between, we don't really care. And we're actually never going to be forced to care about it, except unless we make a mistake, pretty much. And so it's just going to be constant. Okay. So in particular, here's something that relates to some of the warnings I've given before. Suppose you take psi of omega, our big, huge placeholder. Psi of omega is this decently big countable ordinal, phi2 of 0. Add 1 to it. You can always do that. Okay, and remember that successors is the whole driving force of most of this stuff with ordinals. Now take psi of that. Well, by what I just told you, that's just the same as if we hadn't had 1 at all, because we're actually going to be setting psi to be constant as soon as you get to psi of omega until you get to the really big suckers, which is omega. Okay, well, psi of omega, Okay, psi of omega is a fixed point for psi, so that's psi of omega. You might want to pause at this one and just kind of make sure you see what's going on here. Okay, so um, in other words, let's see, psi, this is exactly of the form psi of alpha plus 1. Okay, well, psi of alpha plus 1 suddenly hasn't gotten any bigger than psi of alpha. And so definitely the nth term in the fundamental sequence of psi of alpha plus 1 should not be something bigger than psi of alpha. So this is exactly where this really doesn't work. This always assumes that psi of alpha plus 1 is going to be bigger than psi of alpha. And to sneak up on it, you take psi of alpha itself and you exponentiate it and again and again and again and make a double up tower, an exponential tower. And this just doesn't work anymore. Okay, so um, this might be distressing. And I know when I first started working on this, like, wow, how much is this going to screw me up? So the key is we have to make sure we write expressions in a sort of canonical form again. And in particular, this kind of thing, even though it's a legal application of the functions, it's not a form we would ever want to write things down. And here's the rule, or the most important rule, and that's that when we have a psi inside of a psi, and we're basically composing psi but maybe putting something in between, like this plus 1, what we have to have is that the inner argument has to be smaller than what this whole outer argument, the argument of the outer psi, is going to be. And because psi can decrease things now, that's actually a little tricky. So for example, in our example here, big omega is this big uncountable guy. It is bigger than psi of omega plus 1. And so doing this, psi of omega plus 1 exactly violates the rule. Here's psi of a big guy. Then psi decreases that as an output, and the plus 1 doesn't really help very much. It's still countable. And so then the bigger psi is acting on a smaller input than the psi did, the inner psi did. Okay, so that I predict that's going to be like head scratching. Like, what? Am I going to have to keep track of this through these videos? The great thing is that if we just follow our rules that I'm going to lead you through for creating big ordinals, they won't lead us into that trap. And we have to just kind of accidentally stumble into that trap. So that's a really, really good news, is that we won't actually have to worry about this unless we make blanket statements like this and assume they're always true and then get confused about, like, wait a minute, this doesn't seem to go with the blanket statement. Okay. Last little thing, we never actually explicitly said if we have psi of omega, this first new cool value of psi, what is the g value on that? Well, g of psi of omega of n is, by definition, g of psi to the n of 0. And that's exactly the triple up. And remember what it was when I knew I had k. How far up was this? Okay, yeah. When I had k psi's stacked together, like this guy, it was just n triple up k plus 1. And yet again, we're just diagonalizing. We're just putting in the n there. Okay, let me go down again. Okay, so this is not a bad place to stop. G has really gotten pretty decent. A triple up with n in both slots. And this is the start of the story where psi starts to create some stuff that's pretty impressive and eventually will outstrip Veblen. Okay, pretty long video, a lot of technicalities, but it prepares us for a lot of good stuff in the next one.